Algebra 1. We are moving on in our unit of quadratics, getting to lesson 5, which is building quadratic functions to describe situations, part 1. This week, we're actually going to do parts 1, 2, and 3. I think last week I told you guys I would only assign 2 lessons, but 1, 2, and 3 go really well together, so we're doing 3. First of all, to start with our warm-up. Student task statement says, study the table. What do you notice? What do you wonder? Okay, take a second and look at it and think about what you notice and wonder. Well, I kind of notice that when x increases by 1, y also increases. Okay, not by 1, but it increases. That's one thing I notice. Another thing I notice is that the y values are all values squared. Okay, it's not incremental though. What's 256? I can't remember. Looking it up. Oops. Calculator. 256. 16. And then 400. It's weird. Like even here, I'm not sure. Not looked at the answer key yet. I know. Oh, it's because 144 is not 11 squared. Haha. 144 is 12 squared. That makes better sense. So it looks like we're plus 4 between what we're squaring. Interesting. Okay, trying to find the pattern. That's a cool pattern. What else? We could also say the y values are divisible by 4, 8, and 16. All of them are. Okay, that's 4, that's 2, that's 1. I could take the differences, but it's not going to matter. Like 8 minus 4 is of the actual numbers of these. The successive differences are not constant, so it's not linear. Cool. If we did the factors, we do 16 divided by 64, 64 divided by 144, 144 divided by 256, also not constant. So it's not exponential. Whenever we have these, we know that it's quadratic though. Did we get them all? I think we noticed and wondered a lot. All right, falling from the sky. So what you guys don't know is the motion of a falling object is very commonly modeled with quadratic functions. So here we're going to build a really simple quadratic model or equation using given time distance data of a free falling rock from a building. Do not try this at home. So if we look at this data, a rock is dropped from the top floor of a 500-foot tall building. A camera captures the distance the rock traveled in feet after each second. So our seconds are going up by 1. And our distance is not going up by 1. It increases faster. Okay, you might notice those numbers from our warm-up, right? So what do you think the numbers tell us? I think the second numbers say the camera took a picture every second. And then the feet numbers tell us that the amount of feet is growing. The distance the rock fell grows more with each second than just by a +1 or +4 or plus something. So it's definitely not a linear fall. Okay, a rock is going to get faster as it's falling because gravity helps it out, right? All right, so how far will the rock have fallen after 6 seconds? Show your reasoning. Well, we sort of started talking about it in the warm-up. We sort of figured out that that was 0 squared, 4 squared, 8 squared. I don't know why I wrote an 8 there. Ooh, that was a big eraser. What do we say that was? 16 squared, 20 squared. So at 6 seconds, what do you think our squared is going to be? I think it's going to be 24 squared because we're increasing that base number by 4. So it would be 20 plus 4, which is 24 squared, which is equal, that one I certainly don't have memorized either, 576. Can it fall 576 feet? No, because we have a 500-foot tall building. That's odd. So that means that really it can't fall that far. It has to be 500 feet because it's real world. And the building's only 500 feet tall. So the rock's going to hit the ground before 6 seconds. So Jada noticed that the distance fallen are all multiples of 16. She wrote down 16 equals 16 times 1, 64 equals 16 times 4, 144 is 16 times 9, 256 is 16 times 6, 400 is 16 times 25. That actually makes way better sense than the way I did it, right? Because that would be second 0. You know what? We just need to make this bigger. Did that make you guys dizzy? It was just too small for me even to write on. So this was second 0, wasn't it? Let me go back and look. You have it in front of you. Nope, that was second 1. That makes better sense. 1, 2, 3, 4, 5 seconds. And then she noticed that 1 through 25 are the amount of seconds squared, which is pretty cool. So use Jada's observation to predict the distance fallen after 7 seconds. Well, 7 seconds would be 16 times 7 squared. 7 squared is 49. I do not know what 16 times 49 is. 784. Again, the rock can only fall 500 feet. But that's really interesting, right? I like how Jada thought through that. It was pretty sweet. And then write an equation for the function with d representing the distance dropped after t seconds. So we know the distance is going to be 16 times seconds squared, because that's what we did right there. And then you know what I do every time I write an equation? I test it. I'm not going to lie. 16 for 1 second would be 1 squared, which is 16, which is what we got. 2 seconds, which is 16 times 4, which is 64, which is what we got, etc. I always test it a few times to make sure it works. Let me point out a few things here. What we know is this right here suggests, a quadratic relationship. Okay, that variable squared is quadratic, and that relationship is between the time and the distance traveled. okay? The elapsed time and the distance. So how do you know that the equation d equals 16 squares represents a function? How do we know that represents a function? Okay, it's a really important question. Well, we know that for every input of time, every time we input time into the equation, let's do this. Sorry, I have to make my eraser smaller. I'm going to erase everything. For every input of time into the equation, there is a particular output. For every input of time, there is a particular output. So one input of time equals one output of distance. One input of time, we have one output of distance. And that was a definition of function that we learned way back when, right? So what would we do here? Let me get a blue pen. This is a really important question. If we want to know if the rock will travel 600 feet before 6 seconds have elapsed, how can we find out? We could plug it into our function. D equals 16 times 6 squared. And that would give us 16 times 36, which we already know is too much, 576. 576 feet. Okay, we're going to be going over this for a few days, but you need to know that we only have a few data points to go by, and the quadratic expression of 16t squared is simplified. Okay, quadratic functions are generally used to model the movement of falling objects. We're going to see this expression appearing in some other contexts, okay, where gravity affects the quantities being studied. You're going to recognize some of these numbers because they deal with gravity. And look, our next section is labeled Galileo and gravity. So Galileo Galilei, an Italian scientist, and other medieval scholars studied the motion of free-falling objects. The law they discovered can be expressed by the equation d equals 16 squared. Hey, you guys discovered something that Galileo discovered. That gives the distance fallen in feet as a function of time in seconds. So an object is dropped from a height of 576 feet. How far does it fall in 0.5 seconds? So when I first started learning all this stuff, I would always draw a building first. In fact, I would get fancy and I would draw a person on the building throwing something off of it. So we are dropped from a height of 576 feet. And then we know our function is modeled, d equals 16 times t squared. We can even write it in function notation. So 0.5 squared times 16 is going to be a whopping 4 feet. Okay, and that's just using the function notation. Let's look at the next page. So to find out where the object is after the first few seconds after it was dropped, Alina and Diego created different tables. Alina's table and Diego's table. How are the two tables alike? How are they different? It looks like Alina's table mirrors what we did in the warm-up. Okay, she seems to be using d equals 16t squared. And it looks to me like Diego is going backwards. So maybe Elena's time is time when the rock is thrown from the top of the building or dropped from the top of the building, and Diego's is time before it hits the ground. So they're just gathering data in opposite ways. So time until it hits the ground, they're just recording, they recorded measurements done from opposite ends. Okay, Alina's table starts with 0 feet for 0 seconds, and Diego starts with 576 feet for 0 seconds. Okay, that's our only difference. So alike, time is the same, and then different. Alina's table is going from 0 increased feet or distance, and then Diego is starting at 576 decreased feet. So we could finish filling in the tables. Okay, I'm using the function. I get 144, 256, and 16t squared. Okay, this one would be 16t squared Actually, let's write it backwards. I'll write it in a different way. Okay, when t is 0, that's what I get. So actually I'm taking 576 and I'm minusing, that's a technical term, 16. So this one would be 576 minus 64. 576 minus 144. 576 minus 256. And then our equation. Cool. Awesome. Okay, this last thing is just something for us to review. So this would be Alina and Diego. So Alina started, she has her distance falling, increasing. So at time equals 0, her distance falling increases. And I've got the nice half of a parabola, right? I could mirror it and get the other half of the parabola. And then Diego's is starting at the top and falling down. It actually looks like a rock falling because it's the distance remaining for his fall. All right, that's all for today. We'll continue this on in a second.